4.5 billion years ago, there was nothing here. No earth spinning beneath your feet, no sun burning in the sky above, no planets, no moons, no asteroids tumbling through the cosmic dark. Just an enormous cloud of gas and dust drifting silently through space, so vast it could swallow 1,000 solar systems without leaving a trace. But hidden within that seemingly lifeless void was everything. Every atom that would one day become the ground you walk on, the air you breathe, and the very flesh and blood of your body was floating there in the darkness, waiting for the cosmic trigger that would transform emptiness into worlds. What I'm about to show you is the most incredible construction project in the history of the universe. A process so violent and beautiful that it defies human imagination. We're going to witness the birth of our entire solar system from absolute nothingness to the complex dance of planets we see today. And here's the thing that's going to blow your mind. This isn't some abstract scientific theory. This is your origin story. The star that lights your world, the ground that supports your existence, the very elements flowing through your veins right now, all of them were forged in the cosmic furnace I'm about to describe. But before we dive into the spectacular violence of planetary birth, you need to understand just how impossible this whole thing should have been. The odds against our solar system forming the way it did are so astronomical that most scientists agree we shouldn't exist at all. Yet here we are, and the reason why comes down to one of the most dramatic events in galactic history, an event so powerful it literally shook the stars themselves. Stay with me as we unravel the greatest mystery in astronomy. How did 4.5 billion years of cosmic chaos give birth to the only known oasis of life in the universe? The answer is going to take us on a journey through stellar explosions, gravitational warfare, and chemical alchemy on a scale that makes every human achievement look like a grain of sand on an infinite beach. Part 1: The Stellar Nursery That Almost Wasn't. Picture this. You're floating in the depths of space about 4.5 billion years ago, surrounded by what astronomers call a molecular cloud. But don't let that name fool you. This isn't some wispy collection of water vapor like the clouds in Earth's atmosphere. This is a monster, a dark nebula stretching across dozens of light years, packed with hydrogen, helium, and trace amounts of heavier elements that would eventually become everything solid in our solar system. The temperature here hovers just a few degrees above absolute zero. It's colder than anything you can imagine, so cold that atoms barely move. The density is almost incomprehensible in the opposite direction. If you took all the air in a typical room and spread it across the volume of the entire Earth, you'd get something approaching the density of this primordial cloud. It's essentially a vacuum by any earthly standard, yet it contains more mass than 1,000 suns. For millions of years, this cloud just drifted through the galaxy, slowly rotating, gradually cooling, seemingly destined to remain forever in this cold, dark state. And here's where things get interesting. Under normal circumstances, that's exactly what would have happened. Molecular clouds like this can exist for tens of millions of years without changing. The tiny gravitational attraction between particles is perfectly balanced by the thermal motion of gas atoms and the rotational momentum of the cloud itself. Its cosmic equilibrium, beautiful and utterly static. But our solar system exists because something extraordinary shattered that equilibrium. Something so violent and energetic that it triggered a chain reaction that would ultimately create every world in our cosmic neighborhood. We're talking about a nearby supernova explosion, the death scream of a massive star that had burned through its nuclear fuel and collapsed catastrophically in on itself. When that star exploded, it released more energy in a few seconds than our sun will produce in its entire 10 billion year lifetime. The shockwave that erupted from that cosmic detonation traveled through space at thousands of kilometers per second, carrying with it a cargo of heavy elements forged in the dying star's nuclear furnace. Iron, silicon, magnesium, calcium, all the materials that would eventually become the rocky planets, blasted out into the void at unimaginable speeds. And when that shockwave slammed into our peaceful molecular cloud, everything changed. The delicate balance that had kept the cloud stable for millions of years was shattered in an instant. Suddenly, regions of slightly higher density began collapsing under their own gravity. The cloud started fragmenting, breaking apart into smaller, denser clumps that would each become the birthplace of new stellar systems. But here's the crucial part that most people don't understand about stellar formation. It's not a gentle process. It's not like slowly inflating a balloon or watching a flower bloom. The collapse of a molecular cloud is one of the most violent events in the universe, a gravitational avalanche that accelerates exponentially once it begins. As the cloud contracts, gravity gets stronger, which makes it contract faster, which makes gravity even stronger, which makes it contract even faster still. Within just a few 100,000 years, our section of the molecular cloud had collapsed from a region dozens of light years across to a spinning disk less than 1 light year in diameter. And at the center of that disk, something incredible was happening. The material wasn't just falling inward randomly. Conservation of angular momentum, the same physics that makes a figure skater spin faster when they pull in their arms, was causing the collapsing cloud to rotate faster and faster as it shrank. This is where the story gets really wild, because what we're witnessing is the birth of our sun, but it's not the gentle process you might imagine. The center of this collapsing cloud was becoming incredibly hot and dense as gravitational potential energy converted to thermal energy. We're talking about temperatures climbing toward 10 million degrees, pressures that would instantly vaporize any known material, and densities approaching that of liquid mercury. And then, in a moment that changed everything, nuclear fusion ignited. Deep in the core of this newborn star, hydrogen atoms were being crushed together with such force that they overcame their natural electrical repulsion and fused into helium, releasing tremendous amounts of energy in the process. The star that would become our sun had just switched on, and its nuclear fire would burn for the next 10 billion years. But that's only half the story, because while our proto-sun was igniting at the center of this cosmic disk, something equally remarkable was happening in the swirling material around it. That flattened disk of gas and dust, what astronomers call a protoplanetary disk, was beginning its own incredible transformation. This is where the planets would be born, but the process was nothing like the orderly formation you might expect. The early solar system was a cosmic demolition derby. Particles of dust, some no bigger than grains of sand, were constantly colliding in the disk around the young sun. Most of these collisions were gentle enough that the particles stuck together, gradually building larger and larger aggregates through a process called accretion. It started with dust grains forming pebbles, pebbles forming rocks, rocks forming boulders, and boulders forming the building blocks of worlds. But here's where things get complicated. The protoplanetary disk wasn't uniform. Different regions had different temperatures, different densities, different chemical compositions. Close to the sun, where temperatures soared above the melting point of most materials, only the most heat-resistant elements could remain solid. Silicon, iron, nickel, magnesium, the stuff of rocky planets. Further out, where temperatures dropped below the freezing point of water, ice could form and persist, creating the raw materials for gas giant formation. This temperature gradient created what astronomers call the frost line, an invisible boundary in the early solar system that would determine the fundamental character of every world that formed. Inside the frost line, you get small, rocky planets like Mercury, Venus, Earth, and Mars. Outside the frost line, you get the gas giants like Jupiter and Saturn, along with the ice giants Uranus and Neptune. It's a cosmic sorting process driven by nothing more than distance from our newborn star. But even within these regions, the formation process was incredibly chaotic and violent. As larger and larger bodies began to form through accretion, their gravitational influence started to dominate their local neighborhoods. They began capturing smaller objects, growing faster and faster in a process that scientists call runaway accretion. The rich get richer, and the biggest objects in each region started hoovering up everything around them. This is when things get really intense, because we're not talking about gentle accumulation anymore. We're talking about high-speed impacts between objects the size of mountains, then moons, then small planets. Each collision released tremendous amounts of energy, enough to melt and vaporize rock, creating magma oceans that covered entire worlds. The early solar system was lit up by the glow of countless impacts, a cosmic fireworks display that lasted for hundreds of millions of years. And here's something that's going to surprise you. The planets didn't form where you might expect them to. The early solar system was so chaotic, so dominated by gravitational interactions between growing planets, that worlds migrated vast distances from their original formation sites. Jupiter, our solar system's gravitational heavyweight, probably formed much closer to the Sun before migrating outward to its current position. The ice giants Uranus and Neptune likely switched places at least once during their formation. This process, called planetary migration, explains some of the most puzzling features of our solar system. Why is Mars so much smaller than Earth, despite forming in a similar region? Because Jupiter's early migration disrupted the formation process in Mars's neighborhood, starving the red planet of the material it needed to grow larger. Why are the outer planets spaced so oddly? Because they're not where they originally formed. The violence of planetary formation reached its peak during an event called the Late Heavy Bombardment, a period roughly 4 billion years ago, when a sudden spike in asteroid and comet impacts pummeled every solid surface in the solar system. The moon's crater-scarred face is a testament to this cosmic shooting gallery. Earth was hit just as hard, but our planet's active geology has erased most of the evidence. What triggered the late heavy bombardment? Most likely, it was caused by the final stages of planetary migration when the gas giants settled into their current orbits and destabilized vast populations of asteroids and comets, sending them careening through the inner solar system like cosmic buckshot. But here's what makes this whole story even more incredible. Through all of this chaos, through billions of years of impacts and gravitational upheaval and stellar violence, somehow the conditions emerged that would allow life to take hold on at least one world. The Earth that formed from this cosmic construction project wasn't just another ball of rock. It was positioned at exactly the right distance from the sun to allow liquid water to exist on its surface. It had exactly the right mass to hold on to an atmosphere, but not so much that it became a gas giant. It had a moon large enough to stabilize its rotation and create tides that may have been crucial for early life. The odds against all of these conditions coming together are so small that many scientists argue we're looking at the universe's greatest miracle. But we're just getting started because the formation of the planets was only the beginning of the story. As the late heavy bombardment finally subsided and the solar system began to settle into something resembling its modern configuration, a new chapter in this cosmic story was just beginning. Because while the planets had formed, they were nothing like the worlds we know today. Earth was a hellish landscape of molten rock and toxic atmosphere. Mars was probably warmer and wetter than it is now, with rivers carving channels across its surface. Venus might have been almost Earth-like before runaway greenhouse effects turned it into the furnace world we see today. But the most dramatic transformations were still to come, and they would be driven by forces that most people never think about when they look up at the night sky. The solar system wasn't done with its violent reshuffling. In fact, some of the most important events in our cosmic history happened hundreds of millions of years after the planets had supposedly finished forming. Let's talk about what scientists call the NICE model, named after the French city where it was developed. This isn't some gentle theory about planetary evolution. It describes a period of absolute chaos that rocked the solar system to its core roughly 600 million years after the sun first ignited. Picture this. Jupiter and Saturn, the two most massive planets in our solar system, were slowly spiraling toward each other due to gravitational interactions with the remaining debris in the outer solar system. For millions of years, these two giants crept closer and closer until they reached what astronomers call a 2-to-1 resonance. This means that for every 2 orbits Jupiter completed around the Sun, Saturn completed exactly 1. And when that mathematical relationship locked into place, the gravitational effects were catastrophic. The outer solar system exploded into chaos. Uranus and Neptune were flung outward like cosmic pinballs, their orbits becoming wildly elliptical as they careened through space. The asteroid belt between Mars and Jupiter, which had been relatively stable, was suddenly stirred up like a hornet's nest. Countless chunks of rock and ice that had been peacefully orbiting in the outer reaches of the solar system were suddenly sent screaming toward the inner planets. This is what triggered the late heavy bombardment I mentioned earlier. But here's the thing that's going to blow your mind about this event. It wasn't just random destruction. This cosmic reshuffling actually made our solar system more stable in the long run. Jupiter migrated outward to its current position, where it now acts like a gravitational vacuum cleaner, protecting the inner planets from most incoming asteroids and comets. Without Jupiter's protective influence, Earth would be bombarded by impacts far more frequently, making complex life nearly impossible. But even as this chaos was unfolding, something remarkable was happening on at least one world. Earth was beginning its transformation from a sterile ball of rock into something unprecedented in our solar system, a living planet. The bombardment that scarred the Moon and Mars was actually delivering something precious to Earth's surface: water, vast quantities of it, locked up in comets and asteroids that had formed in the cold outer reaches of the solar system. Every impact that didn't completely sterilize our planet was potentially adding to Earth's growing inventory of the most precious substance in the universe. And it wasn't just water. These cosmic deliveries were bringing complex organic compounds, the carbon-based molecules that would eventually become the building blocks of life. The violence that nearly destroyed Earth was simultaneously creating the conditions that would allow it to flourish. Meanwhile, deep beneath Earth's surface, another process was reshaping our planet in ways that would prove crucial for its future habitability. The tremendous heat generated by countless impacts, combined with the decay of radioactive elements trapped inside Earth during its formation, had turned our planet's interior into a churning ocean of molten rock. This wasn't just geological activity, it was planetary engineering on a scale that dwarfs anything humans have ever attempted. The convection currents in Earth's mantle began driving the movement of crustal plates across the surface, a process we now call plate tectonics. This might sound boring compared to asteroid impacts and planetary migrations, but plate tectonics would prove to be one of the most important features of our planet. It created a global recycling system that would regulate Earth's climate for billions of years, preventing it from suffering the runaway greenhouse effect that turned Venus into hell, or the atmospheric loss that left Mars a frozen desert. But plate tectonics did something else that was equally crucial. It generated Earth's magnetic field. As our planet's molten iron core began to convect and rotate, it created electrical currents that produced a powerful magnetic bubble around Earth called the magnetosphere. This invisible shield deflects most of the harmful solar radiation that would otherwise strip away our atmosphere and sterilize our surface. Mars, being smaller than Earth, cooled down faster and lost its magnetic field early in its history. Without that protection, the solar wind gradually stripped away most of Mars's atmosphere, transforming it from a potentially habitable world into the thin-air desert we see today. Earth's magnetic field is literally one of the reasons you're alive to hear this story. As hundreds of millions of years passed, Earth continued to evolve in ways that seem almost impossibly fine-tuned for life. The Moon, which had probably formed from the debris of a Mars-sized impact early in Earth's history, was slowly spiraling away from our planet due to tidal forces. But in those early days, it was much closer, creating enormous tides that may have been crucial for mixing the chemical ingredients needed for the first living organisms. The sun itself was gradually getting brighter as nuclear fusion processes in its core became more efficient. This should have caused Earth to heat up and lose its water, but our planet's climate regulation systems, driven by plate tectonics and the carbon cycle, somehow compensated for the increased solar output. It's as if Earth had a thermostat that automatically adjusted to keep conditions suitable for life. And then, roughly 3.5 billion years ago, something unprecedented happened. In the warm, chemical-rich pools and hydrothermal vents of early Earth, molecules began organizing themselves in ways that had never occurred anywhere else in the solar system. The exact details are still hotly debated, but somehow, somewhere on our planet, chemistry became biology. The first living organisms appeared, probably as simple single-celled creatures that could harvest energy from sunlight or chemical reactions. This might seem like a small step compared to the cosmic violence we've been describing, but it was actually the most revolutionary event in solar system history. These tiny organisms began changing Earth's atmosphere, gradually filling it with oxygen as a waste product of photosynthesis. The oxygen was initially toxic to most life forms, causing what scientists call the Great Oxidation Event, a mass extinction that wiped out countless species of early bacteria. But that oxygen also opened up new possibilities for life. It created the ozone layer that protects Earth's surface from harmful ultraviolet radiation. It enabled the evolution of complex cells with internal structures called organelles. And eventually, it would make possible the evolution of large, complex organisms like plants and animals, and ultimately intelligent beings capable of looking back and trying to understand their own cosmic origins. As Earth was undergoing this biological revolution, the rest of the solar system was settling into the configuration we recognize today. The gas giants had found stable orbits that would persist for billions of years. The asteroid belt had been cleared of most of its original material, leaving behind only a sparse collection of rocky debris. The Kuiper Belt and Oort cloud, vast reservoirs of icy bodies in the outer solar system, became the long-term storage facilities for comets that would occasionally visit the inner solar system. But even as stability returned to our cosmic neighborhood, the processes of change never completely stopped. Volcanic activity continued to reshape planetary surfaces. Impacts, while much less frequent than during the late heavy bombardment, still occasionally struck planets and moons with dramatic consequences. The solar wind, that stream of charged particles flowing from the sun, continued to interact with planetary atmospheres and magnetic fields in complex ways. And through it all, life on Earth continued to evolve and diversify, eventually giving rise to organisms complex enough to wonder about their place in this vast cosmic story. The atoms in your body have been on an incredible journey. The hydrogen in your water was forged in the first few minutes after the Big Bang. The carbon in your cells was created in the nuclear furnaces of ancient stars. The iron in your blood was scattered across space by supernova explosions billions of years ago. You are literally made of star stuff, assembled through processes so violent and unlikely that your very existence represents one of the most improbable events in the history of the universe. But we're still not done with this story, because the solar system that emerged from this cosmic construction project continues to evolve today, and some of the most fascinating chapters in its history are still being written. The transformation of our solar system didn't end with the emergence of life on Earth. In fact, some of the most dramatic changes were yet to come, and they would fundamentally alter the character of entire worlds in ways that continue to shape our cosmic neighborhood today. Let's jump forward about 2 billion years to when Earth was still a very alien place. The atmosphere contained almost no oxygen, the continents were barren rock, and the only life existed as microscopic organisms in the oceans. But something was stirring in the depths of those ancient seas that would trigger the most dramatic environmental catastrophe in planetary history. And here's the twist that's going to surprise you. This catastrophe was caused by life itself. The culprits were tiny bacteria called cyanobacteria, and they had developed something revolutionary: the ability to harvest energy directly from sunlight through a process we now call photosynthesis. This might sound harmless, but these microscopic organisms were essentially biological factories pumping out a waste product that was toxic to almost every other form of life on the planet. That waste product was oxygen. For hundreds of millions of years, oxygen had been building up in Earth's atmosphere, but most of it was being absorbed by iron dissolved in the oceans, creating vast deposits of what we call banded iron formations. These geological structures, visible today in places like Western Australia, are literally the rust of an ancient ocean, the physical evidence of oxygen's first appearance in Earth's atmosphere. But around 2.5 billion years ago, the ocean's capacity to absorb oxygen reached its limit. Free oxygen began accumulating in the atmosphere at unprecedented levels, and the results were catastrophic. This wasn't just pollution on a planetary scale. This was biological warfare. Oxygen was a corrosive poison to the anaerobic organisms that had dominated Earth for over 1 billion years. The Great Oxidation Event, as scientists call it, was essentially Earth's first mass extinction, wiping out countless species that couldn't adapt to the new oxygen-rich environment. But here's where this story takes an incredible turn. The same oxygen that killed so many organisms also opened up possibilities that had never existed before. Oxygen-breathing life forms could extract far more energy from food than their anaerobic predecessors. This energy revolution made possible the evolution of larger, more complex organisms. The eukaryotic cells that make up your body, with their specialized internal structures and ability to work together in multicellular organisms, were only possible because of the oxygen catastrophe. Meanwhile, that oxygen was doing something else remarkable. High in Earth's atmosphere, ultraviolet radiation from the sun was splitting oxygen molecules and creating ozone, a 3-atom form of oxygen that absorbs harmful UV radiation. Earth was essentially manufacturing its own sunscreen, creating the protective ozone layer that would allow life to eventually colonize the land surfaces. But while Earth was undergoing this biological and atmospheric revolution, the other planets in our solar system were following very different paths. Mars, which had started out with a thick atmosphere and flowing water, was slowly losing its grip on habitability. Without a strong magnetic field to protect it, the solar wind was gradually stripping away Mars's atmosphere. The planet that might once have been a twin to early Earth was transforming into the cold, dry world we see today. Venus was suffering an even more dramatic fate. Early in solar system history, Venus might have been surprisingly Earth-like, with moderate temperatures and possibly even oceans. But as the sun gradually brightened over hundreds of millions of years, Venus began experiencing what scientists call a runaway greenhouse effect. Water vapor in its atmosphere trapped more and more heat, which caused more water to evaporate, which trapped even more heats in a feedback loop that spiraled completely out of control. The results were apocalyptic. Venus's oceans boiled away into space. Carbon dioxide, no longer dissolved in liquid water, accumulated in the atmosphere until surface pressures reached 90 times that of Earth. Temperatures soared to over 450 degrees Celsius, hot enough to melt lead. The planet that was once Earth's twin became a hellish furnace world where sulfuric acid rains fall from clouds of concentrated poison. But the most spectacular transformations were happening in the outer solar system, where the gas giants were still adjusting to their final configurations. Jupiter, our solar system's gravitational heavyweight, was acting like a cosmic shepherd, its immense gravity corralling asteroids and comets into stable populations while protecting the inner planets from bombardment. Saturn was developing its magnificent ring system through a process that scientists are still trying to fully understand. These aren't solid structures, but countless billions of ice particles, ranging in size from dust grains to house-sized chunks, all orbiting Saturn in a disk so thin that if you scaled it down to the thickness of a piece of paper, it would still be over a kilometer wide. The outer ice giants, Uranus and Neptune, were settling into the cold, distant orbits where we find them today. But these worlds weren't the quiet, frozen balls of ice you might imagine. Uranus had somehow been knocked onto its side, probably by a massive impact that left it rolling around its orbit like a cosmic bowling ball. Neptune was generating winds that exceed 2,000 kilometers per hour, the fastest in the solar system, powered by mysterious internal heat sources that scientists are still trying to explain. And beyond Neptune, in the cold outer reaches of the solar system, vast populations of icy bodies were organizing themselves into what we now call the Kuiper Belt and the Oort cloud. These distant regions became the long-term storage facilities for comets, preserving pristine samples of the original solar nebula in deep freeze for billions of years. As these large-scale reorganizations were taking place, something equally dramatic was happening on a much smaller scale throughout the solar system. The moons of the giant planets were becoming worlds in their own right, each with its own unique characteristics and evolutionary history. Europa, one of Jupiter's largest moons, was developing a subsurface ocean beneath its icy crust, kept liquid by the tidal heating generated by Jupiter's immense gravity. This hidden ocean might contain more water than all of Earth's oceans combined, making it one of the most promising places to search for life beyond Earth. Enceladus, a small moon of Saturn, was experiencing similar tidal heating, creating geysers of water vapor and organic compounds that spray from its south pole into space. These geysers are direct evidence of a subsurface ocean and active geology on a world that should, by all rights, be frozen solid. Titan, Saturn's largest moon, was developing a thick atmosphere and weather systems that create lakes and rivers of liquid methane on its surface. It's the only world in the solar system, other than Earth, where liquid flows across the landscape, though the liquid is hydrocarbons rather than water. But perhaps the most significant developments were still happening on Earth, where life was beginning to experiment with new forms of organization and complexity. Around 1.5 billion years ago, something unprecedented occurred in the history of biology. Individual cells began working together in permanent partnerships, creating the first multicellular organisms. This evolutionary breakthrough opened up possibilities that had never existed in the 4 billion years since life first appeared. Multicellular organisms could specialize different parts of their bodies for different functions. They could grow larger and more complex than any single-celled organism. They could develop new strategies for finding food, avoiding predators, and reproducing. The results were spectacular. Life exploded into forms of incredible diversity and complexity. The Cambrian explosion, which occurred around 540 million years ago, saw the rapid evolution of most major animal groups, including the first organisms with hard shells, complex eyes, and sophisticated nervous systems. But even as life was diversifying and becoming more complex, the solar system continued to throw challenges at our planet. Asteroid impacts, while much less frequent than during the late heavy bombardment, still occasionally struck Earth with devastating consequences. The impact that killed the dinosaurs 66 million years ago released more energy than all the nuclear weapons on Earth detonated simultaneously, creating a global catastrophe that reshaped the entire biosphere. Yet life persisted and adapted, demonstrating a resilience that seems almost miraculous. Each mass extinction event, while devastating in the short term, opened up new ecological niches that surviving organisms could exploit. The extinction of the dinosaurs, for example, cleared the way for mammals to diversify and eventually give rise to intelligence. Meanwhile, the sun itself was continuing to evolve. As nuclear fusion processes in its core became more efficient, our star gradually grew brighter and hotter. This should have made Earth uninhabitable, but our planet's climate regulation systems somehow compensated for the increased solar output, maintaining conditions suitable for life through billions of years of stellar evolution. The ice ages that began around 2.6 million years ago represent one of the most recent major changes in Earth's climate system. These weren't random events, but the result of subtle changes in Earth's orbit and orientation relative to the Sun, changes caused by the gravitational influence of other planets over long periods of time. Even today, our planet's climate is influenced by cosmic forces operating on scales of tens of thousands of years. As we moved into the most recent phase of Earth's history, something entirely new appeared on our planet's surface: intelligence. The evolution of human beings represented a completely unprecedented development in solar system history. For the first time, matter had organized itself in such a way that it could contemplate its own existence and origins. This cognitive revolution had consequences that extended far beyond Earth itself. Within just a few thousand years of developing agriculture and civilization, humans were building tools sophisticated enough to study other worlds. We've sent spacecraft to every planet in the solar system and many of their moons. We've landed robots on Mars and Venus, flown through the rings of Saturn, and even landed on asteroids and comets. These missions have revealed that our solar system is far more dynamic and interesting than anyone imagined just a few decades ago. We've discovered active volcanoes on Jupiter's moon Io, subsurface oceans on Europa and Enceladus, methane lakes on Titan, and evidence of past water flow on Mars. Each new discovery adds another chapter to the ongoing story of solar system evolution. But perhaps most remarkably, we've begun to detect planets around other stars, revealing that solar systems are common throughout the galaxy. The formation process that created our cosmic neighborhood has been repeated billions of times around other stars, creating a vast diversity of planetary systems with characteristics we're only beginning to understand. Some of these exoplanetary systems are remarkably similar to our own, with rocky planets orbiting in the habitable zones where liquid water could exist. Others are completely alien, with gas giants orbiting closer to their stars than Mercury orbits our sun, or planets made of diamond, or worlds where it rains glass sideways in supersonic winds. The story of our solar system's formation and evolution isn't just ancient history. It's an ongoing process that continues today and will continue for billions of years into the future. The sun will gradually grow brighter and hotter, eventually making Earth uninhabitable in about 1 billion years. The outer planets will slowly spiral away from the sun due to tidal forces. New asteroids and comets will occasionally impact planetary surfaces, and volcanic activity will continue to reshape worlds throughout the solar system. But the most dramatic changes may come from an entirely new source. As human technology continues to advance, we're beginning to develop the capability to intentionally modify planetary environments. We're seriously discussing terraforming Mars, deflecting potentially hazardous asteroids, and even moving entire worlds to different orbits. For the first time in solar system history, intelligence has emerged that might be capable of directing its own cosmic evolution. The same species that arose from the stellar alchemy and gravitational chaos of planetary formation might now have the power to shape the future development of the system that created it. This brings us to one of the most profound questions in all of science. Are we alone? Is Earth the only world in our solar system, or perhaps in the entire galaxy, where the cosmic construction project succeeded in creating not just planets, but life, and eventually intelligence? The answer to that question will determine whether the story of our solar system is unique or just one example of a process that has occurred countless times throughout the universe. And that answer may be closer than we think, because we're on the verge of technologies that could detect life on other worlds, both within our solar system and beyond. The search for life beyond Earth isn't just scientific curiosity anymore. It's become one of the most urgent questions facing our species, because the implications extend far beyond biology. If we discover that life emerged independently elsewhere in our solar system, it would suggest that the universe is teeming with biological activity. Every star in the night sky might be surrounded by worlds where chemistry has given way to biology, where evolution has been experimenting with forms of organization we can't even imagine. But here's what's going to shock you about this search. We don't need to travel to distant stars to potentially find alien life. Some of the most promising candidates are right here in our own cosmic backyard, hidden beneath the icy surfaces of moons that were dismissed as dead rocks just a few decades ago. Take Europa, Jupiter's ice-covered moon. Beneath its frozen crust lies an ocean that contains more water than all of Earth's seas combined. But this isn't just a static pool of liquid. Tidal forces from Jupiter's immense gravity are constantly kneading Europa's interior, generating heat that keeps the ocean from freezing solid. These same forces create cracks and ridges on the surface, suggesting that fresh water occasionally erupts through the ice, bringing whatever might be living in the depths up toward the surface where our instruments might detect it. The chemistry of Europa's ocean is even more tantalizing. We know it contains dissolved salts, probably similar to Earth's early oceans. The rocky seafloor is in direct contact with the liquid water, creating conditions where hydrothermal vents might exist. On Earth, these underwater volcanic springs are oases of life, supporting entire ecosystems that derive energy from chemical reactions rather than sunlight. If life exists in Europa's hidden ocean, it would represent a completely independent genesis, a second experiment in biology that evolved under conditions radically different from anything on Earth. The organisms living there would have adapted to perpetual darkness, crushing pressure, and an environment that has remained stable for potentially billions of years. They might be nothing like terrestrial life, using different biochemical pathways, different genetic codes, maybe even different basic chemistry entirely. But Europa isn't the only candidate. Enceladus, Saturn's tiny ice moon, is practically advertising its potential for life. The Cassini spacecraft discovered enormous geysers erupting from the moon's south pole, shooting water vapor and organic compounds hundreds of kilometers into space. These geysers are direct samples of a subsurface ocean, and when scientists analyzed their composition, they found exactly the kinds of chemicals that life requires. Even more exciting, the geysers contain molecular hydrogen, which on Earth is a signature of hydrothermal vent activity. This suggests that Enceladus has active geology on its ocean floor, creating the same kinds of chemical energy gradients that powered the earliest life on our planet. Some scientists argue that Enceladus might actually be more habitable than Europa because its ocean appears to be in direct contact with rocky material, providing the mineral chemistry that biological processes require. Then there's Titan, Saturn's largest moon, which presents a completely different kind of biological possibility. Titan has lakes and rivers of liquid methane flowing across its surface, weather systems that create seasonal changes, and a complex atmosphere rich in organic compounds. It's like a frozen version of early Earth, with carbon-based chemistry operating at temperatures hundreds of degrees below zero. Life on Titan would have to be radically different from anything we know. Instead of water-based biology, organisms might use liquid methane as their solvent. Instead of oxygen, they might breathe hydrogen. Their biochemistry might operate so slowly that what we consider a single biological reaction could take years to complete. But the raw materials for such exotic life are definitely there, raining down from Titan's atmosphere and accumulating in its hydrocarbon lakes. Mars presents yet another intriguing possibility, but with a tragic twist. We now have overwhelming evidence that early Mars was warm and wet, with rivers, lakes, and possibly even oceans covering much of its surface. The conditions were potentially habitable for hundreds of millions of years, long enough for life to emerge and establish itself. But then Mars began to die. Its magnetic field collapsed, allowing the solar wind to strip away its atmosphere. The planet cooled and dried out, transforming from a potentially living world into the frozen desert we see today. Yet life, if it ever existed on Mars, might have found ways to survive. Deep underground, protected from radiation and temperature extremes, Martian organisms might still exist in subsurface water reserves or in chemical reactions between rock and the thin atmosphere. The possibility of past or present life on Mars isn't just speculation anymore. We have rovers actively searching for biosignatures, drilling into rocks, and analyzing soil samples for traces of organic chemistry. The Perseverance rover is literally collecting samples that will eventually be returned to Earth for analysis in laboratories far more sophisticated than anything we can send to another planet. But here's what makes the search for life in our solar system so profound. Every organism we might discover would share a common cosmic heritage with life on Earth. All of it would be built from elements forged in ancient stars, assembled through the same processes of planetary formation and chemical evolution. Yet each world where life emerged would represent a unique solution to the fundamental challenge of how matter organizes itself into self-replicating, evolving systems. Finding life on multiple worlds in our solar system would revolutionize our understanding of biology itself. Instead of having just one example of how life works, we'd have multiple independent experiments to compare and contrast. We could begin to understand which features of terrestrial life are universal necessities and which are just accidents of our particular evolutionary history. The implications extend far beyond science. Discovering that life is common in our solar system would suggest that the galaxy contains trillions of living worlds. Intelligence might be equally widespread, meaning that Earth is not unique, but part of a vast community of conscious beings scattered among the stars. But even if we never find life beyond Earth, the search itself is transforming our understanding of our cosmic environment. Every mission to another world reveals new aspects of planetary evolution, new possibilities for how worlds can develop and change over time. We're discovering that our solar system is far more dynamic and interconnected than anyone imagined just a generation ago. Consider what we've learned just in the past few decades. Volcanic activity on Jupiter's moon, Io, is so intense that it completely resurfaces the moon every few thousand years. The rings of Saturn are probably much younger than the planet itself, possibly created by the destruction of a large moon in the relatively recent past. Pluto, once considered a simple frozen ball at the edge of the solar system, turns out to have active geology, nitrogen glaciers, and possibly even a subsurface ocean. Each new discovery adds complexity to the story of solar system formation and evolution. The simple narrative of planets forming in their current orbits and remaining unchanged for billions of years has been replaced by a dynamic picture of worlds that migrate, collide, transform, and sometimes even exchange materials across vast distances. This new understanding is changing how we think about the future of our solar system as well. We now know that planetary systems are not static arrangements, but evolving, interconnected networks where changes in one location can have consequences throughout the entire system. The gradual brightening of our sun will eventually make Earth uninhabitable, but by that time, the moons of Jupiter and Saturn might become warm enough to support surface oceans and potentially complex life. Meanwhile, human technology is beginning to give us capabilities that could influence solar system evolution directly. We're developing techniques for deflecting asteroids, technologies for terraforming planets, and even concepts for moving worlds to different orbits. For the first time in 4.5 billion years, intelligence has emerged that might be capable of directing the future development of the system that created it. This raises profound questions about our responsibilities as cosmic citizens. Do we have an obligation to preserve the natural evolution of other worlds, or should we actively work to spread life and intelligence throughout the solar system? If we discover existing life on Mars or Europa, how do we balance scientific investigation with biological protection? These aren't just abstract philosophical questions anymore. They're practical challenges we'll need to address within the next few decades. The story of our solar system's birth and evolution is ultimately the story of how complexity emerges from chaos, how order arises from randomness, how life finds a way to exist and thrive under the most unlikely circumstances. From a cold, dark cloud of gas and dust, gravitational forces and stellar alchemy created a system of worlds so diverse and dynamic that it continues to surprise us with each new discovery. But perhaps the most remarkable aspect of this cosmic construction project is that it created the conditions for its own comprehension. The same stellar nucleosynthesis that forged the elements in rocky planets also created the carbon and oxygen and iron flowing through your bloodstream. The same gravitational processes that assembled worlds from cosmic debris also shaped the neural networks that allow you to understand this story. You are not separate from the solar system. You are the solar system becoming aware of itself, matter organized in such a way that it can contemplate its own origins and destiny. Every atom in your body has been on a 4.5 billion year journey from stellar furnaces through cosmic catastrophes to the living, breathing, thinking being you are today. The formation of our solar system wasn't just a construction project. It was the universe creating the conditions for its own self-awareness, for matter to organize itself into forms capable of understanding the very processes that brought them into existence. And that understanding is still growing, still revealing new chapters in the ongoing story of cosmic evolution. As we stand on the threshold of becoming a truly spacefaring civilization capable of traveling to other worlds and potentially even other stars, we're also approaching the next phase in the solar system's evolution. For the first time since the planets finished forming, intelligence has emerged that might be capable of shaping the future development of our cosmic neighborhood. The question isn't whether this will happen, but how we'll choose to use these unprecedented capabilities. Will we be wise stewards of the system that created us, or will we repeat the mistakes that have marked so much of human history? The answer will determine not just the future of our species, but potentially the future evolution of life itself in our corner of the galaxy. The birth of our solar system was just the beginning of an ongoing story of cosmic evolution, biological innovation, and now, conscious choice. What happens next is up to us. The next chapter of our solar system's story brings us to one of the most mind-bending revelations in modern astronomy. Everything I've told you about planetary formation, about the violent birth of worlds from cosmic dust and stellar debris, represents just the opening act of a far grander drama. Because while our planets were settling into their orbits and life was taking its first tentative steps on Earth, something extraordinary was happening throughout the galaxy that would fundamentally change our understanding of what it means to be a planetary system. We were not alone, not in the sense of alien civilizations, though that possibility remains tantalizingly open, but in the sense that our solar system was just one of countless planetary laboratories where the universe was conducting the same incredible experiment in world building. And when we finally developed the technology to peek beyond our cosmic neighborhood, what we discovered shattered every assumption about how common or rare our particular arrangement of worlds might be. The first confirmed exoplanet orbiting a sun-like star was detected in 1995, and it immediately broke all the rules we thought governed planetary formation. This world, designated 51 Pegasi b, was a gas giant, larger than Jupiter, orbiting its star closer than Mercury orbits our Sun. It completed a full year in just 4 days, whipping around its stellar companion at temperatures hot enough to vaporize most metals. This wasn't supposed to be possible, according to our understanding of how planets form. Remember the temperature gradients I described in our early solar system? The frost line that determined where rocky planets could form versus gas giants? Well, 51 Pegasi b was a gas giant that had somehow ended up inside what should have been the rocky planet zone. It was like finding an iceberg in a desert, a fundamental contradiction of everything we thought we knew about planetary architecture. But this was just the beginning of our education in cosmic diversity. As detection techniques improved and space-based telescopes began their systematic surveys, we discovered that the universe had been far more creative with planetary formation than we ever imagined. Hot Jupiters, as these close-orbiting gas giants came to be known, turned out to be incredibly common. Thousands of them have been detected, each one representing a planetary system that evolved along completely different lines than our own. Some of these alien worlds are tidally locked to their stars, meaning one hemisphere experiences eternal day while the other endures perpetual night. The day-side temperatures can exceed 2,000 degrees Celsius, hot enough to vaporize iron, while the night side might be cool enough for exotic clouds of condensed metals to form. Imagine weather systems where it rains molten glass sideways in supersonic winds, where the boundary between day and night is marked by temperature differences more extreme than the difference between Earth's surface and the interior of a blast furnace. Then we discovered the super-Earths, rocky planets larger than our world, but smaller than Neptune, orbiting their stars in configurations that have no analog in our solar system. These worlds, typically 2 to 3 times Earth's mass, represent the most common type of planet in the galaxy. Yet we don't have a single example in our own cosmic neighborhood, making our solar system something of an oddball in galactic terms. The implications are staggering when you really think about them. The planetary formation process that created our solar system, which seemed so natural and inevitable when we only had one example to study, turns out to be just one possible outcome among countless alternatives. The universe has been running billions of separate experiments in world building, each one producing unique solutions to the fundamental challenge of how matter organizes itself into planetary systems. Some stars are orbited by diamond planets, worlds where carbon has crystallized under extreme pressure into structures larger than Earth itself. Others host water worlds completely covered by oceans hundreds of kilometers deep with no land surfaces at all. We've found planets orbiting binary star systems where alien beings would see two suns in their sky, and planets wandering freely through interstellar space, ejected from their birth systems to drift forever in the cosmic dark. But here's what's truly remarkable about this explosion of exoplanet discoveries. They're not just cataloging the diversity of possible worlds. They're revealing the fundamental processes that govern how planetary systems form and evolve throughout the galaxy. Each new detection adds another data point to our understanding of the cosmic construction project, showing us which aspects of our solar system are typical and which are genuinely unusual. The orbital migrations I described earlier, where planets like Jupiter moved substantial distances from their formation sites, turn out to be incredibly common. In fact, most planetary systems show evidence of significant migration events that completely reshuffled their original architectures. The difference is that in many cases, these migrations were far more dramatic than anything that occurred in our solar system. Imagine Jupiter migrating all the way down to Mercury's orbit before stopping or being ejected from the solar system entirely. These extreme migration events explain many of the bizarre planetary configurations we observe around other stars. Hot Jupiters are probably gas giants that migrated inward from the outer reaches of their systems, either stopping at stable orbits very close to their stars or being completely consumed by stellar atmospheres in the process. This discovery revolutionized our understanding of planetary system architecture. What we once thought of as the natural, inevitable arrangement of worlds turns out to be the result of incredibly complex gravitational interactions that could have proceeded very differently under slightly altered conditions. Our solar system's relatively stable, well-spaced arrangement of planets is not the cosmic norm, but rather a somewhat unusual outcome of the planetary formation process. The habitable zone concept, that narrow range of distances from a star where liquid water can exist on a planetary surface, has also been dramatically expanded by exoplanet research. We now know that tidal heating, the same process that keeps Europa's subsurface ocean liquid, can create habitable conditions far beyond the traditional habitable zone. Moons orbiting gas giants in the outer reaches of planetary systems could maintain liquid water oceans for billions of years through gravitational heating alone. Even more intriguingly, we've discovered that red dwarf stars, which are much smaller and cooler than our Sun, can maintain habitable zones for trillions of years. These stars, which make up about 75% of all stars in the galaxy, burn their nuclear fuel so slowly that they could potentially support life for time periods that dwarf the entire history of our universe so far. If life can evolve around red dwarfs, then the galaxy might remain habitable for thousands of times longer than previously thought. The atmospheric compositions of exoplanets have revealed another layer of cosmic creativity. We've detected worlds with atmospheres made primarily of water vapor, others dominated by exotic compounds that don't exist naturally anywhere in our solar system, and some with atmospheric pressures so extreme that the distinction between gas and liquid becomes meaningless. One planet appears to have an atmosphere made largely of vaporized rock, created by temperatures so high that solid matter simply cannot exist on the day side. These discoveries are forcing us to completely rethink what we mean by habitability. Life as we know it requires liquid water, but life as it could be might thrive in liquid methane, liquid ammonia, or even in the exotic high-pressure environments found in the atmospheres of giant planets. The universe might be teeming with forms of biology that are so different from terrestrial life that we wouldn't even recognize them as living organisms. The search for atmospheric biosignatures on exoplanets is pushing the boundaries of what's technically possible with current instrumentation. The James Webb Space Telescope and other advanced observatories are beginning to analyze the chemical compositions of exoplanet atmospheres, looking for the telltale combinations of gases that might indicate biological activity. Oxygen and methane together, for example, create a chemical disequilibrium that on Earth is maintained only by living processes. But interpreting these atmospheric signatures is proving to be far more complex than initially anticipated. What looks like a biosignature might actually be the result of exotic geological processes or atmospheric chemistry that doesn't occur anywhere in our solar system. We're essentially trying to diagnose the presence of alien life using only the faintest chemical whispers carried by starlight, a challenge that pushes both our technology and our theoretical understanding to their absolute limits. The sheer scale of exoplanet diversity is overwhelming when you consider the implications for life in the galaxy. Conservative estimates suggest there are at least 100 billion planets in the Milky Way, with perhaps 20 billion of them located in the habitable zones of their stars. Even if life is incredibly rare, arising on only one planet in a million, that would still mean 20,000 living worlds in our galaxy alone. But the diversity of planetary environments suggests that life might be far more adaptable than we've assumed based on our single terrestrial example. If organisms can survive in the extreme conditions found in Earth's deep ocean trenches, in acidic hot springs, or in the radiation-soaked environment of nuclear reactors, then perhaps they could also thrive in the exotic conditions found on exoplanets. The discovery of thousands of exoplanets has also revealed something profound about the cosmic construction project itself. Planet formation appears to be an incredibly robust process that occurs around virtually every type of star under an enormous range of conditions, from massive blue giants that burn through their fuel in just a few million years to tiny red dwarfs that will shine for trillions of years, from metal-rich stars in the galactic center to metal-poor ancient stars in the outer halo. Planets form wherever there's sufficient material and time for the accretion process to operate. This universality of planet formation suggests that the raw materials for worlds, and potentially for life, are distributed throughout the galaxy and probably throughout the entire universe. The same stellar nucleosynthesis that created the heavy elements in our solar system has been operating in billions of other stellar nurseries, creating the chemical ingredients for countless other experiments in world building. The timeline of exoplanet formation also reveals something remarkable about cosmic evolution. Some of the planets we've detected orbit stars that are much older than our Sun, meaning they had billions of additional years for evolution to operate. If life emerged on any of these ancient worlds, it could have developed complexity far beyond anything we see on Earth. The galaxy might contain civilizations that arose when our solar system was still a cloud of interstellar dust. Conversely, we've also detected planets around very young stars, worlds that are still in the violent early phase of formation that our solar system went through 4.5 billion years ago. These systems give us direct observational access to the planetary construction process, allowing us to watch in real time as worlds assemble themselves from cosmic debris. The protoplanetary disks around young stars show incredible diversity in their structure and composition. Some are smooth and symmetric, suggesting orderly planetary formation processes. Others are warped, clumpy, or show clear signs of ongoing gravitational chaos as massive planets carve gaps and spiral waves through the disk material. We're witnessing the same violent, beautiful process that created our own worlds, but in thousands of different variations. Perhaps most remarkably, we've begun to detect what appear to be planetary systems in the process of complete disruption. Stars with debris disks that look like the aftermath of massive collisions between planetary bodies, systems where planets are being torn apart by tidal forces or consumed by their expanding stars. These observations remind us that planetary systems, including our own, are not permanent fixtures, but temporary arrangements of matter that will eventually be recycled back into the cosmic inventory. The discovery of exoplanets has fundamentally changed our perspective on our place in the universe. We're no longer unique, no longer alone, but part of a vast community of worlds scattered throughout the galaxy. The cosmic construction project that created our solar system has been repeated billions of times with endless variations on the same fundamental theme. Yet this knowledge also highlights just how remarkable our particular arrangement of worlds really is. The stable, long-lived planetary system that allowed complex life to evolve on Earth over billions of years appears to be relatively uncommon in galactic terms. Most planetary systems show signs of dramatic instabilities, close encounters between planets, or other disruptions that would make the long-term evolution of complex life extremely difficult. Our solar system's architecture, with its well-separated planets in nearly circular orbits, its protective gas giants that shield the inner worlds from excessive bombardment, and its long-term stability over billions of years, represents a somewhat unusual outcome of the planetary formation process. We're not unique, but we're also not typical. We exist in what might be called the Goldilocks zone of planetary system architecture, not too chaotic to prevent life's emergence, not too stable to prevent the environmental changes that drive evolution. This realization adds another layer to the cosmic perspective that emerges from understanding our solar system's formation. We're not just made of star stuff assembled through gravitational processes. We're the products of a planetary construction project that succeeded in creating conditions suitable for the emergence and long-term evolution of complex life, something that appears to be relatively rare, even in a galaxy filled with worlds. The ongoing search for potentially habitable exoplanets and atmospheric biosignatures will likely answer one of the most profound questions facing our species within the next few decades. Are we alone in the universe, or is life a common outcome of the cosmic construction project? The answer will fundamentally shape our understanding of our place in the cosmic order and our responsibilities as potentially the only known intelligent species in our corner of the galaxy. But regardless of what we discover about life elsewhere, the story of exoplanet formation and evolution has already taught us something crucial about the nature of cosmic creativity. The universe is far more inventive, far more diverse, and far more dynamic than we ever imagined when we thought our solar system was the template for how planetary systems work. The Cosmic Construction Project is ongoing throughout the galaxy, creating new worlds even as you read these words, experimenting with new configurations of matter and energy, new possibilities for the organization of cosmic materials into complex, structured systems. Some of these experiments will fail catastrophically, producing systems that quickly destroy themselves through gravitational instabilities. Others will succeed in creating stable, long-lived arrangements of worlds that could potentially support the emergence and evolution of life. And in the deep future, when our sun has exhausted its nuclear fuel and our solar system begins its final transformation, the Cosmic Construction Project will continue. New stars will ignite in stellar nurseries throughout the galaxy. New planetary systems will assemble from the debris of ancient worlds, and new possibilities for the organization of matter into complex structured systems will emerge from the ongoing creativity of cosmic evolution. The birth of our solar system was not a unique event, but part of an ongoing galactic process that has been creating worlds for over 13 billion years and will continue for trillions of years into the future. We are temporary participants in an eternal cosmic drama, conscious matter that emerged from stellar debris to contemplate the very processes that brought us into existence. So here we are, 4.5 billion years later, the universe's most unlikely success story, from a cold, empty cloud drifting through space to a living, breathing world teeming with intelligence, capable of looking back and understanding its own cosmic origins. Every atom in your body, every thought in your mind, every breath you take is the direct result of the most spectacular construction project in the history of the universe. The odds against this happening were so astronomical that most scientists agree we shouldn't exist at all. Yet here you are, made of star stuff, assembled through gravitational chaos, refined by cosmic catastrophes, and somehow conscious enough to grasp the magnificent improbability of your own existence. You're not just observing the universe, you are the universe becoming aware of itself. But this story isn't over. Right now, as you've been listening to this, new worlds are forming around distant stars. The same processes that created Earth are playing out thousands of times across our galaxy, each one a unique experiment in cosmic creativity. Some will fail spectacularly, others might succeed in ways we can't even imagine. And for the first time in 4.5 billion years, intelligence has emerged that might be capable of directing its own cosmic future. The question isn't whether we'll explore other worlds or search for life among the stars. The question is whether we'll be wise enough to do it right. The universe spent billions of years creating the conditions for consciousness to emerge. What we do with that gift will determine the next chapter in the greatest story ever told.